Okay. Some of the groundwork for this work has already been laid from the standpoint of vertical asymptotes. Okay. What is going to be new is the horizontal asymptote. That's going to be, which is not hard. It's just there are either some like 3 rules you got to remember with it. Finding x-intercepts is just as usual, and finding y-intercept is just as usual. And then checking the end behaviors of the graph is something maybe new, but it's not crazy. I think putting number 1 through 5 all together to produce a graph is what's difficult, but it's each individual component is not overly difficult, I don't think. But it's very overwhelming to try and do one of these questions from scratch, which is what I think this lesson is going to take us through one of these questions, okay? And then you'll have some time to work on some, and we can just take a couple up. But 2 days, I would think, of this, okay? Just to get the hang of these steps. So finding vertical asymptotes as well as identifying holes in the graph as well, okay? Those two go hand in hand, okay? So vertical asymptotes, we know from our work for simplifying rational variable expressions that the denominator can never be what? Zero. Good. Okay, that's a big part. Why is my pencil not working? So it can never be 0. Okay, this means we need to identify the values in which the denominator becomes 0. It's at these values of x where the vertical asymptotes exist. Okay, and we looked at this distinction of vertical asymptotes versus holes. Both of them are restrictions. I suppose maybe we could put on that line like restrictions and not just vertical asymptotes. But so for instance, if we take a look at this example, relatively straightforward, okay, hopefully, okay. Factor the denominator. What is in the denominator right now? What kind of factoring, Gabe?
X squared minus 1.
Yeah, but what kind of factoring am I going to use to simplify it, right? Yeah, Nick? That's a difference of squares. Okay, so we're going to get x squared by x plus 3, x minus 3. Okay, where x can't equal -3 and +3. Is that okay? So, in all the simplification work we've done, there have been instances where I was able to divide something out between the numerator and denominator. That would have been what we would have classified as a hole in the graph, which doesn't happen in this question. So any of the restrictions that remain at the very end, after you're simplifying, are what we deem as vertical asymptotes. Okay, and they take on an equation, like your axis of symmetry. Your axis of symmetry is an equation of a vertical line, whether or not you knew it. You may have written x equals, or you should have been writing x equals whatever the number is. That's an equation of a vertical line. It's just an axis of symmetry. That's what these are. Okay, they're equations of vertical lines where they occur at x equals -3 and x equals +3. Okay, so this helps us produce the graph, knowing these two vertical asymptotes. Okay, that should not be new, hopefully. Okay, if it is, we might need a little bit more work on the simplification processes, but that's that. Okay, that's a big important part of how to produce these graphs. Okay, so the horizontal asymptotes, you'll recall at the very beginning of this unit we had a discussion around the degree of a polynomial, and that becomes important here. Okay, so when trying to figure out the horizontal asymptotes, if there's multiple ones, we need to look at terms with the highest degree both in the numerator and denominator. Okay, so you're basically looking at the degree of the numerator and comparing it with the degree of the denominator. Okay, and there's a few rules that come with this in order to produce where the horizontal asymptote is. So the highest degree in the numerator is, for this question that we're working on right now, is what? What's the degree of the numerator? Basically, how many variables, and I don't mean like x, y, z. I mean like how many variables are in the numerator. That's the degree. Yeah,
2.
it's 2, right? Because it's x squared. So the degree of the numerator is 2. And what's the degree of the denominator? Remember, now we have 2 terms there. And the degree of a polynomial always takes on the term with the highest degree. So what is it, Robbie?
2.
There's 2 again. We see that? This has the 9 has a degree of 0. Okay, but the polynomial as a whole has a degree of 2 because of that x squared. We see that? Okay. So we'll try to keep this up until we can see it. So when the degree of the numerator is less than the degree of the denominator, the horizontal asymptote is going to be 0. Okay. Horizontal asymptote. What's the equation of a line? What's the equation of a horizontal line? Because is it x equals? It's y equals. So basically what it means, if I drew you a sketch right now, like let's say I had a horizontal asymptote at 1. What's the equation of that? Here, horizontal. Horizontal meaning left and right. Everyone good with that? Left and right. It's occurring at 1. Everybody see? What's true about all points along that red line? Just so everybody never makes this mistake again. What's true about all points along that red line? Gabe?
They're on the y-axis 1.
Yeah, they're every single point along that red line is going to have a y value of 1. It doesn't matter what the x value is. All points are going to have some x value and a y value of 1 everywhere. Over here, we're going to have another number in 1. Here we see? So the equation of the horizontal asymptote is going to be y equals something. In this particular instance, when it's 0, it's y equals 0. Okay, here it would be y equals 1. Everyone following okay so far? Okay. Each, like I said, each individual component I think is reasonable to follow along with. I think when you put all 5 together and it's expected you produce a graph, that's when things start to get awry or go awry. Okay, when the degree of the numerator is equal to the degree of the denominator, the horizontal asymptote is, this one's a little more complicated. Is this or is this not the instance of what we have right now? So the degrees of the numerator and the denominator match. The coefficient in each of them is 1. Would everyone agree? Of the leading term? This is important. So we have 1x squared over 1x squared minus 9. So when the degrees match, the horizontal asymptote takes on, or is equal to, the ratio of the coefficients in front of the leading term. Okay. Okay, this one here is a grade 12 thing. Okay. But it's important for you to know. We're not going to draw any of these right now. We're not going to do questions like this, but you will do it in grade 12 if you take the grade 12 advanced functions. Okay. This is what's known as, if the degree of the numerator is greater than the degree of the denominator, the horizontal asymptote isn't really horizontal, it's oblique. So it basically means it's some sort of asymptote. It's just an equation of a line, but it just goes off, it's oblique. Just something like that. Okay.
So basically, y equals mx plus b.
Yeah, it's y equals mx plus b. Yeah. Okay. That's good. So I've been telling my grade 9s, like, doesn't matter what level of math you take, like, we're seeing lines over and over and over again in different different capacities, if you will, right? And it doesn't matter which math you take, all the way up to grade 12 calculus, like, you're gonna be doing the equation of a line between 2 points, which is way back when. That's a grade 9 question. It doesn't go away, right? Because as we saw, ultimately what we're interested in calculus is, like, if you think back to the last, like, unit test when I'm asking you to figure out, like, a secant versus a tangent, that is calculus. And finding the slopes of those lines, that's rate of change, which is what calculus is. Okay, and we represent rate of change with lines, either instantaneously or over 2 points, which would be an average rate of change. And a lot of the time it's with, like, speeds, instantaneous velocity, average velocity, things like that. But they're just lines. Okay, so this idea of, like, oblique asymptote is just another application of your grade 9 linear work, if you will. Okay, so here's some examples here. So let's state the horizontal asymptotes. Okay, so important for you to recognize the degree of each of the numerator and the degree of the denominator, and then match it up with one of the rules up top. So what are you seeing in the first one? What's the degree here?
1.
That's a good. The degree is 1. Okay, and what's the degree in the denominator? Yeah, the degree in the denominator is 2, right? Because of that x squared there. Okay, so which scenario am I in? 1, 2, or 3? It's the first one, right? Where it says the degree of the numerator is less than the degree of the denominator, and therefore the horizontal asymptote is going to be y equals 0. Okay, again, they're just lines, right? This one's a horizontal line, and the vertical asymptotes are just vertical lines. Okay, yeah. Okay, what about in the second one? Degree here. What's the degree in the numerator? Dylan?
2.
That's 2 again. So it's squared. Remember, degree is talking about the number of variables you can, how many repeated multiplications there are, if you will. Okay, because it's x squared, there's x times x, that's a degree of 2. Okay, what about the degree of the denominator? Remember, this is a polynomial now, so it's, remember the rules around polynomials.
Wouldn't it be 3?
Is it, okay, so remember, I'm going to remind you of the very first lesson. The degree of a polynomial takes on the term with the highest degree, which is why we write things in descending order, because it's very apparent very quickly as to what the degree is, because that's the term with the highest degree. Okay, and so that's going to be also a degree of 2. And what do we do if the degrees match, numerator to denominator? What kind of horizontal asymptote do I get? Yeah.
Take the ratio of the coefficients.
Yeah, you take a ratio of the coefficients. So up top, we're gonna get 4/2 for the coefficients. Okay, so your horizontal asymptote here is gonna be y equals 2. Okay, again, there's just, each step has its own little nuancy things that you have to remember.
It's not supposed to be fraction.
Isn't that what? What's the matter?
Over A, or H
Oh, sorry. No, it's not a fraction. It's just I was just classifying the horizontal asymptote. Okay. So, what about the question that we're building here and ultimately going to graph at the end of the lesson? X squared over x squared minus 9. What's the horizontal asymptote there? What is it?
2.
The degree is 2 in each of them, yes.
Does not make it.
So you're looking at the degrees, and then when you identify that the degree is matches in the numerator denominator, you take a ratio between the coefficients.
Yeah,
What are the
but it does equal 2.
The degree is 2, yes, but the horizontal asymptote is not 2. The coefficients here are what, Dylan?
1,
1 and 1. So the horizontal asymptote is y equals 1. Okay, everybody see, it's not crazy, but it is going to get crazy when you put all 5 steps together.
They're the same.
Okay? Okay, so finding, is everybody okay?
If the degrees are the same, you divide them over.
The rest of this work should look familiar. It doesn't matter what the function is. Like, you should be able to find x-intercepts and find y-intercepts. That's grade 10 work. Okay, this stuff, I will give you credit, it's a little bit tricky. Okay, the simplification of the expressions, which is what we spent last week looking at, as well as the identification of the horizontal asymptote. Like, that takes some time to get your head around the rules. Okay, so let's just spend some time looking at those statements here, 1, 2, 3. If you know that, that helps. Okay. Okay, so finding x-intercepts. So you're going to recall the y value of any point along the x-axis is always what? It's always 0. Okay, any x-intercept is going to have a y value of 0. Okay, so that's what we're going to do. We're going to substitute 0 for y, and we're going to solve for x. Okay, so in that particular instance, the root 0 solutions for the values, and set the numerator equal to 0. Okay, those are our x-intercepts. Okay, so the x-intercept for x squared over x squared minus 9 here. I'll show you the work here, just so everybody's on the same page. Does the denominator matter? Is, I guess, maybe my question. Like, in the interest of solving for x, what would you do? If I multiplied both sides by x squared minus 9, what are you going to be left with?
Minus, wait, no, never mind. X squared minus 9 equals x squared.
No, because
What's 0 times anything?
Oh, yeah.
This is that's good. It's good Dylan's asked about that, because it's hitting home the point I'm trying to make here. The denominator is irrelevant when finding the x-intercepts. Because when you multiply both sides by the denominator, the 0 is just going to consume it. You're just going to be left with 0 equals x squared. Right? The denominator doesn't play a role in finding x-intercepts. It does play a role in finding y-intercepts, but that's a different situation. We'll look at that in a second. But x-intercepts is just the numerator. And so sometimes in the numerator you can have a trinomial that you can factor and get 2 x-intercepts. Just like everything we've done for the last year and a half. Okay? So in this particular instance, what value of x makes this left side equal right side true? Gabe?
0.
Yeah. So the x-intercept here is going to be 0. So that means in a point, or a coordinal point, it's going to go through the origin, right? Because I put in the fact that y was equal to 0, and solve for the x value that made that true. Well, that was 0 as well, just coincidentally in this particular question. Okay, so this graph is going to go through your origin of 0, 0. Now, what's true about a y-intercept? You got to flip-flop. So in your mind, you got to flip-flop between like x-intercepts and then y-intercepts. So what's true about all values of x along a y-intercept? Yeah.
X is equal to 0.
Yeah, so x is equal to 0 for y-intercepts, right? Hey. Okay, so put in 0 for x and see what you get for y. Remember, that just means I'm evaluating the function at 0. Sometimes they'll give you a number other than 0, sometimes it won't. Okay, doesn't change what you're doing, right? So when I substitute this in here, I get 0 squared over 0 squared, should put that in brackets, sorry, minus 9. So I get 0 over negative 9, which is 0. Are we okay? This part of the test I'll let you have a calculator for, because I think when we turn the page over and we start looking at end behaviors, we need the calculator for that. I don't expect you to do that without a calculator. Okay? Everybody okay? So just to recap, we're finding vertical asymptotes the same way we have by simplifying the expressions and stating restrictions. Any of the restrictions that cancel out in our simplification process are deemed as wholes. Anything remaining at the very end of our simplification is a vertical asymptote. Okay, then we're mixing in this idea of horizontal asymptotes, and that's a ratio. What could be a ratio of the coefficients, or it could just be 0. You got to look at those 3 rules that are on that piece of paper. Then we're layering in our solving for x-intercepts and our y-intercept. Those are the 4 things. So it's number 1, 2, 3, and 4 that we've done so far. Okay, number 5, now that you've marked all that stuff out, is actually strategically, all we're going to do is substitute values of x into the function and see what spits out for y. And then we're going to mark those points, and then from that we can connect the points and produce the graph. That's all that's happening. But what I'm doing is I'm not picking random x values to substitute into the function. I'm going to pick specific ones. Okay? Specific ones around my restrictions. Okay? We're going to check end behaviors. Oh. You're right. Yeah, sure. Thomas, you see the world. Wait. Wait, are we good? Okay. So we're gonna pick. I think the first column is just kind of some numbers that we can just kind of pick. The second ones are maybe a little bit more geared towards what our restrictions were. Okay, so you'll recall our vertical asymptotes were what? Can you remind me what the vertical asymptotes were?
0.
That was the x-intercept. Asymptotes, restrictions. What were the restrictions for the graph? Gabe?
X couldn't equal negative 3 or
Okay, good.
positive 3.
Okay, good. So the vertical asymptotes are going to occur at x equals positive 3 and x equals negative 3. Okay? So I'm going to start with those ones. And what I'm doing is I'm checking where is the graph, because I know we cannot cross vertical asymptotes. They're like restrictions. So they kind of contain the graph into a particular area. Okay, what I'm going to do is I'm going to check where is the graph on either side of the restriction. Does that make sense? So right here I'm checking the graph on the right side of 3.5, and I'm checking it on the, on the right side of 3, which would be 3.5, and I'm checking it on the left side of 3, which would be 2.5. And you could pick anything. You could pick 2.9999, and you could pick 3.001. But you cannot input 3 because that's going to break the function, as we've seen. You're going to get a 0 in the denominator. Okay, so the first thing I would do when you do these questions is I would plot the restrictions of the vertical asymptotes. So let's plot those first. I'll do those in red. Okay, so I'm going to plot the restrictions, all the asymptotes. Let's do that first. Okay, so x equals 3 is going to be here. This is going to be a vertical asymptote. Here, I'll thicken that up. Everybody okay so far? That's how you would graph a vertical asymptote. Okay. I know the graph cannot touch those values. Okay, so I'm using that fact to figure out where is the graph over here, where is the graph in here, and where is the graph over here. Because I know it can't touch those values. So we've kind of broken it into 3 chunks. Ever see that? So what I'm going to do, okay, just so everyone's on the same page, I'm going to pick some value of x on the right side of this, and I'm going to pick some value of x on the left side of it. I'm going to input it into the function. It's going to give me a y, a new point. Then I can plot that point and figure out, if I do that a couple times, I'm going to get an idea of where the graph's going on either side of stuff. Okay? I'm going to do the same thing here. I'm going to check on the right side of 3 and on the left side of 3. The left side of 3 is going to be 2.5. On the right side of 3, this is going to be x is equal to 3.5. You see what I'm doing? Just going to input values. It's just function notation. It's just the numbers are not going to be nice here, which is why you're going to have your calculator. Okay, which I might need your help for here as we work through here so people can type in stuff. Okay, on the right side of -3, I'm going to have -2.5. And on the left side, I'm going to have x equals -3.5. Okay, now let's also plot our horizontal asymptote. Where was the horizontal asymptote? Can you remind me? Yes, the horizontal asymptote. What's the equation of a horizontal asymptote? Just remind me. Y equals, it's good, y equals 1. Okay, so let's go plot that, and then we're good. Now there's one rule: you can cross horizontal asymptotes, but you can never, ever, ever cross a vertical one. Okay. What did we say? I guess we do know, technically right now we know 1 point. Unfortunately, it's 1 and not 2. We know 1 point that's on our graph right now. What is that point? What?
0, 0.
Yeah, it went through the origin, right? Ideally, or not ideally, but like in some of the later questions, you could have 2 x-intercepts and a y-intercept, right? And then you'd have 3 points on your graph. Okay, but for right now, we know that we went through 0, 0. So I'm just going to plot that point. This is 0, 0 is both for this question specifically, our x-intercept and our y-intercept. So it has to go through that point. So what do you want to start with? Why don't we start with where the graph is around our vertical asymptotes? That's maybe a good start. So what's the value if I substitute in, and maybe I have some of these written down. I do. I have, if you input f, and remember we're referencing our function here is f of x is equal to x squared by x squared minus 9. So I'm just going to make a little list. I don't necessarily need to see all this work, but I would like you to write down if you evaluate f at 2.5, I'm going to get out negative 2.27. You can check that on your own. So all I'm doing is 2.5 squared divided by 2.5 squared minus 9. That's negative 2.27. So what do I do with that? This is a point, right? Everyone agree? 2.5 is my x value, and negative 2.27 is my y value. So I can go plot that. So go plot it. 2.5 and negative 2.27. 2.5 and negative 2.27 is going to be down here somewhere. Here, maybe I'll highlight the point so you can see where stuff came from. Okay. Okay, let's do another one. Gabe, you got a question? You're stretching.
Oh, it's stretching, sorry.
Okay. What if I evaluate on at negative 2.5? Okay, if I evaluate there, I get the same thing. Let me see. So now I'm going to go plot this point. That's going to be over here somewhere, right here. That should be enough for you to produce that graph. What is that in the middle? Coincidentally, it's just what? It does this, look. Did we talk about what asymptotes were? The graph gets closer and closer and closer to them, but never touches. So where does that look like it's getting? Like if I put in negative 2.9999, it's going to be closer and closer and closer to this. So in the middle section, that's what my graph's going to look like in the middle. Okay, I don't have numbers for f at 3.5 and f at negative 3.5. Somebody wants to do those, but I do have f at 7. If you evaluate the function at 7, you should get... do you need to see this? Are we okay? It's 7 squared. It's not letting me right there. I'll do 1 just so we all know what's going on. 7 squared minus 9, which is going to be 49 by 40, which gives me a result of 1.225. Okay, what I'll do is I'll plot that in green. Sorry. So at 7, when I input the value of 7, 7 is 1, 2, 3, 4, 5, 6, 7, I get a value of 1.225. If I evaluate at f equals -7, I get negative. Oh, sorry. No, I don't. I get positive still. Okay, I need 2 more points and then I get an idea. Okay, Gabe?
15.
Say that again? 15? Oh, yeah, sorry, I put in 15. 15 is maybe a little overkill. I'm not really worried about that per se. I'm more worried, like, what part of the graph right now do I not really have any information on? Dylan?
On the right side of the graph.
Yeah, I'm missing some information in here. Like, I don't know where the graph is in there. Like, it could very well be up here. It could also be down here because I'm allowed to cross over horizontal ones. So what I'm trying to figure out right now is whether or not my graph does that or if it does this. You can cross over horizontal, but you cannot cross over vertical. Vertical are like real problems, right? They like cause havoc in the denominator of the function. It gives you a reference point, I think. So I'm interested in some sort of value in here. I don't know where it is, so why don't you substitute into your function 3.5? Because if I put in 3.5, that's 1, 2, 3.5. It's either going to spit me out down here, the y value, or it's going to be up here. I just need a y value to plot a point. And then once I have that point, I can connect it. And I'm going to do the same thing over here because this is the piece of the graph I'm missing right now. Here or here. So I'm going to substitute 3.5 into my function. And negative 3.5. So I just need those values. I need the evaluation at 3.5 and I need the evaluation at negative 3.5. I don't have those on my page. Somebody's got to do this for me. I can tell you where they are. I don't know what the values are. They are up here. I just don't know what the value is. Unless someone wants to tell me. They come out to be positive. Oh, when did you get it?
I got 12.25 for 3.5 squared.
All right. So, oh, okay. Yeah. So sometimes just being able to tell whether or not something's positive or negative, I don't necessarily need the exact point. I just need to know whether or not the graph is positive or negative in that area. So just go ahead.
3.76923076.
That's for 3.5?
Yeah.
3 point what?
3.76.
3.8. Okay, so and I'm assuming the other side's gonna be 3.8 as well. Okay, so when I substitute those values, I'm gonna get 1, 2, 3 point, almost there, and 1, 2, 3.8, almost there. Okay, so my graph is gonna look like this. That's it.